To the panel on network science, and this will be moderated by myself and Professor Tara Javidi, who is sitting here. We heard a lot about network science these days. We had an opening talk from one of the funding agencies that talked us about what we should do research about, and we had a plenary talk on network science and also several tutorials that focus on the theoretical aspects. So the objective of this panel is to brainstorm a little bit more informally on what this network science actually is and what we are trying to construct. So to do that, we have put together a great team of commentators. Let me briefly introduce these people to you, and then we'll go on with the questions that Tara will give them, and then we'll ask for contributions from the audience. The first contributor from your left is Professor John Kleinberg, who gave us a wonderful plenary lecture yesterday. And Alex already made a great introduction to him yesterday, so I don't know what to add. He's a recipient of MacArthur Foundation Fellowship and is a National Academy of Engineering member, and he has so long list of prizes that he wants that would be too long to remember, and he's a professor at Cornell. After him, we have Debasis Mitra, who I would define him as an Indian intellectual from Calcutta. He was the head of the Mathematics of Networks Center at Bell Labs from 1996 to 1999. And he's also a member, elected member of the National Academy of Engineering for contribution to communication systems. And he has his own share of prizes that are too long to comment upon. Right after him, we have Alain Barrat, who is a research scientist at CNRS, and he is representing here the young and upcoming crowd. He's also here representing the old world, Europe, and he was a student of Marc Mézard, and he is bringing ideas from statistical physics into the modeling of networks, and we hope to have his comments on this. Then we have Balaji Prabhakar, who's a professor at Stanford, and he has his, as usual, his own share of prizes, like the Informs Applied Probability Society Prize, Rollo-Davidson Prize Award, and so on and so forth. And he's recently undergone this effort to understand suicidal networks. Suicidal networks. And hopefully we'll learn about that. And finally, to conclude, we have at the very end of the table Professor Don Tosley from University of Massachusetts at Amherst, and he is a great contributor not only to the theory but also to the practical aspects of systems. He has the honor of being both a fellow of the IEEE and the ACM, and he received the 2007 ACM Sigmetric Achievement Award and 2008 SIGCOM Award, among a continuing and never-ending list. All right, once I sort of try to intimidate the audience with all this introduction, I hope to get your full participation with comments and questions for the speakers. Just to get things started, I'll hand it over to Professor Tara Javidi, who will ask some first introductory questions, and then we'll give it to you.
So, hi everyone, thank you for coming. What we did earlier on, we sent a list of questions, 5 questions to our panelists and asked them to think about them and have opening statements. So I'm going to go through the questions, then ask our panelists to actually address them. In the very unlikely event that their opening remarks will not cover these questions, I will actually, pose the questions directly to them, but that's very unlikely. Then I'm hoping that all of you will help me actually, with the rest of the session to ask the more interesting questions. So the first question we asked them was to tell us if network science is indeed old or new, and what is the history or what are the various historical contexts that we should be aware of. The second question was, and this is Massimo's attempt at being more controversial, if network science is more math, engineering, or science, or I guess maybe more physics, or is it all of those? The third question is, if you would be teaching a course in network science, what would you teach? So that's the third one. The fourth one is, if we were successful at building a network science, what would be the impact on system development and beyond? And especially to this audience, what are the impacts beyond networks of information? And finally, and this is somehow related, is network science different from information science? Are they the same? And what are the roles of information theory, if there is any, in network science? And with that, I will ask Professor Devasis Mitras if Dr.
Thank you. I want to begin by thanking Alon and his co-organizers for inviting me. It's a rare pleasure to see so many old friends from Bell Labs and universities from all around the world. It's a tremendous experience. Thank you. Now, what you will think after this presentation is another matter, because I have blithely chosen to ignore these questions. I'm sure it'll come to haunt me later, but I really just wanted to talk about some problems that are raising its head, that's dominating our thinking. So indulge me, and maybe there's a connection, I think there is, with network science. And so the perspective here is that of an industrial research laboratory, actually a little more specifically Bell Labs. So it's not academic. There's a difference between research of industrial research and academic research. And in fact, the industry in this case is very specifically telecom. So the first thing I wanted to talk about is energy efficiency in communications. Now, in many ways, it's a surprising thing to talk about because telecommunications only uses about 2% of all the energy consumed, so why bother? But in fact, it's growing. It's growing, and we want it to grow even faster than the way it is because there is hopefully a substitution from other energy-guzzling sectors like car transportation and airplane transportation into communications. So there's a multiplier effect here that might explain why there's such a multifaceted drive to try to bring energy efficiency into telecom much more than it is today. So the background is that about the middle of January, only about 2 weeks ago, there was a launch of an initiative called Green Touch. You can look it up, greentouch.org. It's a consortium of essentially 4 or 5 constituencies. There's the network operators, there are the system vendors, and Alcatel-Lucent is an example of one such. Semiconductor component builders like FreeTouch, and research institutes like INRIA in France, and finally universities there. So there are 15 consortium members. And based on some calculations that were done in Bell Labs, which hopefully will become public knowledge. This consortium announced a very bold goal of achieving a 1,000-fold increase in energy efficiency in telecom in 5 years. Now, as to whether it's so it's an educated guess. It's apparently doable and certainly very necessary if you buy any of the climate control, the carbon footprint theories that the analysis that's around. So what I'll do is, so 1,000-fold gain. Now, there's a bit of a roadmap. So a lot of this is just research. So there's work to be done. So this community is a sort of community that hopefully will be engaged. But the roadmap has, in my opinion, roughly 3 main thrusts. The first is small cells in wireless access. And why so? Well, it really is starting with the propagation loss being proportional to distance raised to a certain power, like 3.5. Right? Small cells addresses that. Now, to this community and to the wireless industry, it's an old story in some sense, but small cells have been tackled from the point of view of capacity. Not necessarily, and witness femtocells, for example. But the thrust here is really at energy efficiency, and that has a whole set of new issues around it. And certainly 2 that come immediately to mind is what about all that network management? Femtocells don't have to deal with people moving around from one cell to another, but now if it's going to really be the base of mobile telecommunications, you will have to worry about network management. So what about the energy cost of that? And of course, the other big elephant is backhaul. So who's going to do the backhaul? Is it going to be optical? But that would mean covering the United States with optical fiber, or is it going to be wireless, in which case you are up against the old problem of propagation loss. A whole bunch of open issues to be addressed. But anyway, that's a direction that initial analysis seems to indicate promise. The second one is wireline. So, wireline, you really should think about transmission, routing, switching, routers and switches. Here, optical is the gold standard, right? Every time you do a little less electrical, every time you don't have to go from optical to electrical, back to optical, using a router, you're a winner in this in the energy game. Now, all optical networks is not a new topic either. That's been around, but it's still elusive. And one reason people have looked at this. There are very hard mathematical problems associated with design of all optical networks. They tend to be inevitably integer programming problems and intractable as a consequence. The third line of attack in this energy efficiency is really what can be lumped as architecture, algorithms, and protocols. There's a rough indication is that 1 in every 30 packets is only useful in the initial protocol. Everything is wastage. So certainly protocol redesign offers hope. Content-centric networking seems to be exactly the right direction to go because it's exploiting multicasting and storage. And there's a whole slew of other ideas. Now, 1,000, though, is a very large number to do, and as to whether all this will work or not is an open question. Now, I did want to talk about a second problem that interests me greatly, but perhaps in the interest of time, I'll skip it. I'll just mention what I had meant to talk about. It was a concept called virtual telco as an example of cloud computing. And it's got a lot of people in Bell Labs and elsewhere and many other places quite energized. And because it's a specific case with enough meat and payoff, you can focus ideas instead of talking very generally about cloud computing, which seems like a absolutely great idea on resource sharing. Right? But perhaps Balaji will talk about it. I think he might. The next item that I feel passionately about, and I think I hope you will as well, is this issue of balancing managed services and best effort within the framework of net neutrality. Right? It is an issue that the FCC is grappling with right now, the rulemaking for it in the context of the open internet and specifically net neutrality. So it's a topic that really matters. It'll, what the FCC decides will have very large impact, and I think there's a certain obligation we have to try to do to make so that the right decisions are made. So best effort, of course, is what's dominant right now, and the internet that we know rely on, and love is really based on best effort. However, managed services is already there. It's not and the examples, it's not ubiquitous. It's not it's small compared to best effort, but voice over IP and IPTV are examples of managed services that are already out there and established. And there's a whole set of managed services concepts waiting in the pipeline for the work. And an example of that is just e-health, monitoring and rapid response with e-health. So managed services, as you can imagine, has to do with quality of service. And quality of service in terms of reliability, very high reliability in some cases, like 5 nines that the telcos are used to, security, and availability. Right? So that and of course, one is expected. The assumption is that premium prices will be charged for subscription for getting these managed services. Now, what the FCC, well, not the FCC, what we all have concerns about are really at least two. One of them is that you allow managed services and you open the floodgates, and the resources that are available for best effort will get squeezed, and it'll get dominated by managed services. That's certainly a concern. And the other one is that the network operators will deliberately deteriorate best effort service with the goal of inducing subscription to premium prices. Right now, that's just concerns, and there must be. Now, it turns out that there's the two sides to the coin. Managed services require best effort because the population of best effort is really the potential subscribers for managed services. Without that best effort, I don't think managed services can survive by itself. Secondly, the innovations for managed services are really coming from the best effort. There's a certain belief we have that the rate of innovation for managed services is proportional. It's some way dependent on the size of the best effort population. So there is a. Now the other side is that there are curves indicating that the cost per subscriber for best effort is climbing, right? And within a very short period, of the order of 2 years or so, it's going to cross the subscription fee. At which point, or even before that, obviously, because everything is predictive, you'll have a real drawdown of investment for best effort services. So if everything is left alone, the route is towards the tragedy of the commons. Right? Now, I think there's a tremendous scope for modeling and innovative solution over here, and no analysis really is complete without having a dynamic element to it. There's this aspect of revenues and profits being plowed back into the infrastructure has to be part of any analysis that's done, and there's a real paucity of that right now. right? And there's all kinds of interesting proposals that one can think about, such as one of them being something like the Universal Coverage Fund that existed under the old Bell system, where some amount of funds from the profitable part was used to subsidize the rest, which is not profitable, for universal coverage. In any case, it's an area crying out for modeling, analysis, and inventive solutions. I think I'll end here. I think I've taken my time. Good.
Thank you.
Bear with me while I connect. Okay, I think what I'm going to give you is probably more of an academic view of network science. I should mention that although if somebody were to ask me in the hall, let's say over the last few years, do I work in network science or not, I would have glibly said yes. But this is really the first time that I've been asked to sort of think about what it is. And so what you're going to have to bear with me. This is the result of, let's say, several hours. And in fact, I'm hoping to refine my view of it as we go through this panel. So I guess I think of it as sort of the study of dynamic interacting networks, okay, with the emphasis really being on dynamic and interacting. And if you go to Wikipedia, that's what they would say. The NRC report that came out 5 or 6 years ago does the same thing. And really, what we would like to do as part of this is to understand the dynamics of interactions, and with the hope that it might lead to better designs. And of course, we have all kinds of networks that interact with each other, technological, the phone network that, let's say, Debastis has been very much involved in, the internet, power, road networks, societal networks, and Topology, I guess, we'll be talking about these. It could be financial, online, social, terrorist networks, and so on and so forth. When I think of sort of driving forces here, I guess first and foremost, and this is speaking for myself, it's really intellectual curiosity, okay? It turns out that when you think about, let's say, the idea of interactions between the networks and the fact that they can change at a variety of timescales, it just brings up a fascinating set of questions that we really haven't addressed in the past. The other thing about this is that, and I think part of the reason why network science is sort of very much, let's say, being talked about, is that there's just a huge availability of data. In fact, there's really more data than one knows what to do with. And in fact, what I would sort of say is that the internet and the web are sort of a common substrate for many of the networks that people are interested in. And what it has led to is that anyone can jump in, PhD student, a researcher at a lab, a faculty member, and essentially get data and start playing around. Now, I'll sort of come back to that a little bit because there's some issues that arise there that are sort of important to understand. I guess another driving force, but it's probably sort of secondary for me, is really designed for robustness. And sort of a classical example that one might give is you have a cyber attack on the internet, and the question is that it could affect financial networks, it could affect transportation networks, that attack can essentially affect many of the networks. And so understanding what the interactions are and, of course, designing so that you have robustness in the face of these kinds of attacks is clearly important. Here's another driving force. It turns out that about 6-7 years ago, the Army Research Directorate got very, very interested in this. And they have a very clear focus on their part. They want to understand how to build robust networks that can be used in command and control, can be used in the field. And in fact, they were really sort of important stimulants for, let's say, the first NRC report that came out. And I thought I might mention, in case some of you may not be aware of this, they actually set up a research program, Network Science CTA, which in the fall of last year ended up to the funding of 4 network science centers. And the idea was that they were thinking of a layered approach, but not layered in the way that, let's say, my network colleagues might think of. But you've got, a physical substrate. You essentially have to develop a communications network on top of it. And then you have information flows that are running on top of that. And then, of course, sort of the intent of, let's say, the users on top of that, social cognitive. And so what they did was they ended up funding 3 centers corresponding to the top 3 substrates, and then a 4th center that is supposed to take and mold what comes out of those 3 into something that is useful. And really the focus here is really on interaction of the substrates. And so I think of this as sort of a very interesting driving force. When I think of challenges, I'm going to just say this is sort of mom and apple pie, clearly modeling, control, design. And what I want to do, though, is I want to talk a little bit about what I've been sort of interested in the context of networks. And that is empirical network characterization, okay? And it turns out to be challenging because of the size of some of these networks. The fact that if you look at something like, let's say, the internet, it's really divided into lots of smaller networks. There's no centralized authority, so there's no place, no repository you can go to essentially get data or characteristics of the network, which makes it really very, very interesting. And so, for example, one of the empirical studies that took place, let's say in the late 90s, and is sort of helped mold at least the networking community in this area, was that of topology characterization. And so I'd like to talk just a little bit about that. Okay, the idea is you have the internet, you have no idea what it looks like inside, but you can do measurements. Okay, and so somebody came up with the idea of using the traceroute tool, which is a common tool in the internet, to essentially sort of sample paths within the internet, and then to take those paths and essentially construct a sampled network. Okay, so out comes some sort of a time series, and then you take the data and you look at it and you sort of try to determine the characteristics of the internet. And so what came out of this was the notion that if you plotted let's say the degree distribution, for example, in a log-log plot, it was a straight line. And so all of a sudden there was this sort of very important result that the router topology exhibited a power law, and that perhaps a variety of models that had been proposed previously, let's say in the physics world, could be applied here. Okay, and I'll just say that essentially stimulated a number of studies that supported the conclusions of the initial study. There were people who then went and they developed models that supported this conclusion. Okay, and then a few years later, somebody decided to try the following Gedanken experiment, and they said, let's take a topology which we're going to construct such that it has an exponential degree distribution, and let's just see what happens when we run this kind of let's say, sample trace route on top of it. So they did. They got the data. They did the destination, and the question is, what came out of it? Well, there was a power law degree distribution. And so therefore, the conclusion, of course, from this was that exponential degree distribution was essentially the same as a power law distribution. Okay, and of course what happened after that was that then another group of people came along and they started modeling this particular way of trying to characterize the internet, and they found that in fact the models could explain that you could have something starting with exponential and it could come out with a power law, and then in fact that was an artifact of not the internet itself but of the sampling method. Okay. And so really what you want, and a reasoned way of doing this, is that there is some perhaps unknown degree distribution, and let's say you do take the sample trace route methodology, but what you need to do is you have to have a model for what's going on, both a model, let's say, to start off of the internet, and then a model of how the sampling will generate, let's say, particular kinds of measurements. That has to then feed into a reasoned estimation, and then with the hope that, of course, you'll come out with the appropriate degree distribution. The other way, of course, is that perhaps the problem is with this sort of sample trace route, and then what's important is to then come up and design an appropriate sampling methodology for which perhaps it's easier to sort of extract the models of the network and the sampling so as to be able to come up with the distribution. Okay, so one of the things that I've been sort of trying to argue for is the need in the context of, let's say, network science, of a network measurement science, okay? Because of the fact that in network science, we're dealing with very large, complex networks. It's very important to be able to gather good data and to be able to, let's say, do good empirical characterizations. And what I have been noticing is that there's a lack of rigor that characterizes many of the empirical studies that have come out. Looking at social networks, for example, there are many studies that essentially draw erroneous conclusions. Sometimes they do, and they know they're erroneous, but they don't know what else to do, and so they still put it out. Others don't realize that they're erroneous. And so it essentially poses a real challenge to, let's say, practitioners of, how do you go about characterizing network dynamism, let's say, in an empirical way? How do you capture interactions, let's say, among various networks? And of course, what's really needed is sort of a principled approach for doing these kinds of empirical studies. Okay, and I'll stop here.
Okay, thanks. I'll try to be brief, all the more so because I already consumed an hour of your time yesterday standing right here. So as I said in my talk yesterday, I mean, I guess one perspective I also want to represent in this panel is this idea that there's really this convergence of the human aspects of networks and the technological aspects of networks, right? And that I think what we're seeing when we confront these design problems is the interplay of these two forces in ways that challenge, I think, each community separately, the ones that have thought about technology and the ones that have thought about human populations primarily. One way to think about that, and actually one way to think about the question, what is network science, or why are we calling it network science, is actually, I think back to things as mundane as faculty recruiting committee meetings that we have where we talk about areas that we're looking at, and someone will say networks and someone will say networking, and there's a sort of careless use of terminology, but actually when you think about it, networks versus networking is actually an important distinction because one's a noun and one's a verb, right? And the point is really that a lot of what's been going on with network design and with the design of the internet protocols has really been the verb form of networking. And the verb is increasingly crashing into the noun, right? The fact that there are these network properties that emerge that we don't fully understand, but that we have to take into account from a design point of view. And in that sense, it's sort of, at this point, it's almost moot to ask, is this hybrid of technology and human phenomena something that we want to study? Should we try to get into this area? Should we move into this area? Is it a good area? All of those increasingly become beside the point because it's being forced on us by the way these systems actually operate, right? So if you look at the design of any of these modern large information systems, including the ones that have been used as examples thus far, they're inevitably controlled by human forces that we don't fully understand, but that we have to, in some sense, get right in order to make the system work. And viewed that way, I think, things such as the interaction of computer science and with economics, the rise of these areas that are variously called algorithmic game theory or CS econ, are sort of inevitable next stages in the design of algorithms, right? So speaking as someone with a computer science background, you know, the development of thinking about algorithms has never been static, right? There's never been a one working definition of algorithms. Rather, we once upon a time had standalone algorithms that you ran on your standalone computer. Those moved to parallel and distributed algorithms. They moved to algorithms that had adversaries, cryptographic algorithms, secure algorithms, online algorithms, and adaptive algorithms that didn't know the future. All of those things, approximation algorithms and heuristics when problems were intractable, all of these were actually in rapid-fire succession next steps in the evolution of algorithms. And it's only inevitable that a step beyond that is algorithms where the units that you're operating with are not things that you can program, not things where you can implement protocols exactly, but operate under their own incentives, right? Because they're people or because they're organizations. And so rather, part of algorithm design has to be to apply these indirect force fields that cause them to do things in desirable ways. So I think that's sort of going to be a big challenge. I think in some sense, a lot of what we call network science arises out of that tension. And in some sense, it's not going to be easy to actually bring all these communities together, because I think in a sense there are several cultural boundaries between them, right? So as a computer scientist talking with economists, on the one hand, it's a fascinating activity because they also speak in a sort of, you know, the economic theorists anyway speak to the CS theorists in a similar language. We both like discrete math. We both like simple mathematical models. We both, in a way, are talking about artifacts that have been created by humans, right? Big computing systems on one hand and economic systems on the other, and yet that we don't fully understand and that we have to understand their basic phenomena better. However, there are also big differences, right? So one thing about, I think, the CS community, the information theory community, electrical engineering, networking, and so forth, is that we tend to work bottom up. We build things, we use those as building blocks to build more complex things, we build even more complex things, and gradually we have to reason about these complex things that we've built, but everything proceeds bottom up. We encounter the phenomena as we develop them through building, right? That's obviously a simple approximation, but it describes a lot of activity in these fields. Economics and areas like that work in a different way. There are certain macroscopic phenomena that you see. You see them happen. But you don't understand necessarily why they happen. And so you often develop models top-down, right? You start with this phenomenon that you have to explain, and you develop increasingly refined explanations. And in a top-down field, you're less concerned, for example, when certain aspects of your model may be inconsistent with other aspects of your model. Because you're sort of keeping the observation fixed, and you're coming up with increasingly refined models, right? So in the same way that people coming from a mathematical background would find it inconceivable that you could be working with a model where you know that conclusion A contradicts conclusion B, right? That would, in mathematics, that would be a signal to stop, roll back to where you made the mistake and go forward again. That's somehow not only inevitable, almost necessary in some of these fields where you're developing observations and you're testing out theories, right? It isn't a good thing, but it's hard to find a better alternative. Okay, so I think another interesting question is the validation of these models, and this has been raised in a number of talks and also in what John was saying, that we see a lot of talks that say, here's a network phenomenon, and here's a model that reproduces that network phenomenon. And I think those kinds of results are extremely interesting. And I think what we have to resist, of course, is to make the false conclusion that, therefore, this model is a good reflection of reality, right? That model is designed as a good reflection of the single data point you observe, the single phenomenon you observed. And in fact, it's a wide open research question to actually formalize what does it mean that this network model captures this network that I'm observing, right? That's a hard problem in any area of science, but I think it's one where, particularly in the context of networks, that there are so many different network invariants and network properties. We're not going to possibly explain networks one invariant at a time. It can't be that first we get the degree distribution right, and then the diameter, and then the spectral properties, and so forth, and that eventually, after enumerating 10 or 12 of these, we've got the network right. A network doesn't work that way. And so I think actually having a richer, more formal theory of what it means for a model to capture a network phenomenon is something that's really desperately needed. And it's going to have to come out of some synthesis of a number of different communities. Okay, a final point. You guys wanted me to talk about if I were to hypothetically teach a course on networks, what might be in it. So in fact, this is something I've been thinking about for a while. And at this point, it's a subject actually that I think works very well both at a graduate level and at an undergraduate level. And it's something where there can't be one course that covers everything that even all of us panelists have talked about, right? You have to focus on particular aspects of it. And in particular, when I teach it, because I'm not a systems person, there's a relatively small amount of how to build systems, because that's not something where, you know, within my department, I would have the most intelligent things to say about it compared to my colleagues. So it's more at the level of building models, running algorithms to analyze what's there. And I think there's a whole companion side of teaching, which I wouldn't be able to talk about as thoroughly on actually building network protocols and designing them. But at the level of building models and building algorithms to analyze data, I think there are a number of areas that feed into this, right? So there's this sort of hybrid of probabilistic, algorithmic, and combinatorial reasoning that I think both information theory and the theory of computing really excel at, right? That's sort of hybrid of probabilistic, combinatorial, and algorithmic, which is a style of thinking more than any particular results that are really essential for thinking about this area. Secondly, I think one needs some amount of statistics and machine learning, right? Because with this enormous amount of data, one has to understand what does it mean to draw conclusions correctly from it, what does it mean to build models and validate them, again, similar to things Don was talking about. And finally, and especially when I've most recently been teaching this at the undergrad level, co-teaching with an economist, David Easley at Cornell, I've really come to appreciate the power of incorporating models from game theory and from economic theory into our thinking about this. Because in the end, those supply us with many interesting hypotheses about behavior, and in particular about the way behavior is altered when you apply certain forces to the network, right? So this notion that when you make a change to the system, you can't evaluate how that change will happen taking everything as fixed, because everything won't remain fixed. Everything will change, right? And in some sense, I think computer scientists often get this wrong because we come from this bottom-up world where you design things, right, to get back to my original point. And in a bottom-up world where you design things, when, for example, you create an internet search engine that ranks pages based on links, and then people go and create link farms, and they create web spam, and they create clusters of things that try to look like important pages, then in computer science we dismiss these people as malicious, as adversaries. We create fields with names like adversarial information retrieval, because somehow those people aren't doing what they're supposed to. We were supposed to be evaluating documents in a certain way, and they refuse to behave. That's kind of a perverse view of things. You could ultimately view it as it's inevitable that when you announce to people how you're going to evaluate them, they're going to go and behave in ways that do well for that evaluation. That's, in fact, how all of us behave when we apply to grad school, apply for jobs, come up for tenure, and so forth. And so you have to think about the system with those feedback loops built in. And I think that's not something that computer science has really thought about as much until the last 10 years or so. It's something which feels like economics have had much more practice at. And so again, I think incorporating those perspectives into such courses are very useful also. And I'll stop there. Thanks very much.
Okay, thanks for inviting me to this conference and to the panel. And I would like to start talking about network science, or maybe rather what I like to say, to talk about is the field of complex networks, because network science has been criticized because of using the term science. And a few keywords that to me are very important is, first of all, interdisciplinarity. Of course, it can sound trivial, but in fact, it's really a field in which you get to talk to people with very different backgrounds, and I'm not so sure it's so common. It's a very broad field in which you find people coming from biology, from computer science, from statistical physics, from mathematics, etc., etc. And the other keyword that has already been mentioned several times is that it's a data-driven field, in the sense that we have gone from graph theory to network science because of the availability of such large amounts of data, and the fact that, of course, also about because of the idea that very different systems could be represented as graphs. And this is, of course, also thanks to the very abstract idea that is behind a graph. I mean, it's very simple, it's very abstract, so potentially it could be applied to many things. The point that has really helped to go into this direction is the fact that there is data. So, and data coming from different fields, so from the web, from the internet, from biological networks, etc., etc. So, of course, afterwards, you have to ask the question, was that useful to represent these systems as networks? And that's probably still a quite open question. If I give some lectures sometimes about an introductory course about complex networks seen from a statistical physics point of view, and the way I structure it is always going from a first chapter about the empirical data and the fact that this data has stimulated the development, the definition of new tools, be them statistical or more precise, to characterize the structure of networks, such as the heterogeneities there are in this network, the community structure, etc. And this has really stimulated whole fields, subfields of research towards the characterization. And of course, these tools have given feedback to the field by showing that in these very different systems there were common characteristics. I mean, community structures, you find them in many, many different networks, from metabolism networks to social networks, etc. Heterogeneous degree distribution are found quite commonly. And then the second chapter I talk about usually is about modeling. So indeed, and it's still driven by the fact that we have data, because since we have found that there are some characteristics that are common among many networks, but were not most often within the most famous graph theory paradigm, which was the Ardashirani network, then there have been, of course, ways to extend these random graph models, or to find new modeling frameworks which try really to understand how these characteristics, which are common to so many different systems, could have emerged in maybe some simple common mechanisms. So once again, even when we are talking about very simple mechanisms, which could be very schematic, there's behind the idea that it's stimulated by the data and what the data have shown us. And the largest chapter is about the study of how the structure of these networks have influence or impact the way that dynamical phenomena which occur on these networks are evolving. So it can go from very simple or toy models, such as random walks on the network, to more applied models, which even applied models such as epidemiological models, in fact, can be can be described through relatively simple reaction diffusion models, which are very well known in statistical physics, and actually they are used in epidemiology. And one of the most striking results in this area is the way that the epidemiological threshold is behaving in networks. So basically, the epidemiological threshold separates, depending on the parameters of an illness, a phase in which the illness will propagate among the population from a phase if the illness is not propagating fast enough, or if people are recovering fast enough, the epidemics will die out. So if you have the hypothesis which was most commonly used beforehand, which was of homogeneous mixing in the sense that more or less all people were equivalent, then you have these epidemiological thresholds that can be computed. Now, if the epidemic is spreading on a network which is heterogeneous, for instance, with a power law degree distribution, but more generically with a heterogeneous degree distribution, then you find that the epidemiological threshold is almost going to zero. It's going to zero in the large size limit, and it's in fact much smaller than if you have the homogeneous mixing hypothesis. So this is one of the examples in which really having looked at the data can help really understand what's going on in a real phenomena, in which if you had put the homogeneous mixing hypothesis that you had lacking other information, you could really not understand what's going on. So here I would like to mention a few ways in which I see the field evolving in the present years, actually. And to me, there are two very different directions. Up to now, I've been talking about things that are very generic and in which basically people have tried to come from different disciplines and find common grounds, common tools, common mechanisms. Now I think there is one direction which is somehow going back down the separate fields of research, maybe informed by this intense communication which has taken place between the fields. And this is certainly the case, in, for instance, in epidemiological studies, in which now it's possible to build models of spreading of epidemics at the worldwide level, but it's possible to do it not just because we have the big computers and we could simulate 6 billion people, because that would be just a very large agent-based model in which you have lost every control of what you're doing. It's possible to do it by integrating several a lot of information about the data of transportation networks, because it's basically this way that epidemics are spreading around the globe, about the information of how reaction diffusion models behave on complex networks, such as the transportation networks. So it's possible to do it with a fundamental understanding of the theoretical behavior of this kind of models. So you can do large-scale simulations, and you have also a fundamental understanding of what's happening. For instance, it's possible to show that just from simulations, you can show that if you have an epidemic spreading over the globe, then cutting down the air transportation system by 50% will not help. And it has been shown that from a theoretical point of view, this has been explained. Whereas at first it was coming a bit as a surprise from the simulation. And it has been shown through works by people who had worked on complex networks. So the other kind of directions I see are the following, and are still at a generic level. For instance, the one is the fact that networks have often been seen as isolated entities, but in fact, they are often coupled between them. So how do we deal with networks which are coupled? How do we deal also with the integration of networks? And this relates to John Kleinberg's talk, in which we have social and technological networks which are interplaying, and how are they correlated? How can we measure these correlations? How does that affect? How does one network affect the other, etc., etc.? Another direction is the fact, and it's linked also to the coupling of networks, is the fact that we have multi-scale networks. So for instance, if you think about transportation, we have air transportation network, which is at large scale, but you have also commuting networks, transportation networks, and how do you integrate these different scales? And finally, and it's the one aspect I'm most interested in now, is the fact that we are often dealing with dynamical networks, which are evolving on very different time scales, possibly. And this is true with social networks, both at a large time scale, like just friendships, in which they can evolve on time scales that are of years, let's say, but also quick encounters social networks, like the interactions in a conference, so which can vary on the scale of minutes. And how do we deal with this dynamicity? And here I would say that in all these cases, we are back to square one, in the sense that we are back to empirical characterization, and we can open again all the questions that have been asked before for static networks. And I think that is really one very important direction of research. So we'll stop here. Thanks.
Hi, everybody. Good afternoon. So let me start by just doing a broad general purpose introduction to this question of what is network science. As someone who does networking, I've sort of grown with this thing where networks didn't used to be big, and so it was called technology, because you're building this stuff yourself. And then at some point, if you see the papers, say from the 80s to the 90s to the 2000s, what you see is that people say things like tens of thousands of nodes. Okay, that was like considered a big network in the 90s. This was like a big deal. In the 80s, it was thousands of nodes. Okay, and then now it's passé to say billions of nodes. So nobody says it, right? Now, what's happened as the size has grown is that this is escaping. We've lost the control, in the sense that, when we build something, we know what we're building, and when we build it and put it out there and it gets so big, it's doing things that we're trying to understand. So I think somewhere there is where it became science, because science is trying to understand phenomena that are out there, and if you created it, hopefully you knew enough to understand it, but now that this thing is out there, you've lost it, right? So that's how I view science as coming into this. So it isn't something we're trying to glorify our activity by throwing science on it, but rather it is genuinely the case. The other way in which I see this as being a science is that there's this sort of small microscopic things making massive having macroscopic effects. That's the other way in which things have changed pretty dramatically. And so, for example, I don't know why we don't say, we should start saying, I believe, financial science. Right? It stopped being a single bank. It's not a network of banks sitting on Wall Street. It's around the world. So I think it's reached that stage where the people who come up with small microscopic financial instruments have this massive consequences that they're shocked that this has happened. And so I think that's how the science comes in. So that makes it interesting, I think. And the rest of the presentation, since the societal networks has been introduced as a topic and it's something I'm interested in, I thought I'd at least let some people know, those of you who weren't at a talk I gave on Monday, quickly get a sense for what it is. And so I have just about 3 slides on it, and I'll tell you about it. So I guess I have to set the displays again. Give me a second, please. So, and I have just a few slides on both societal networks and data centers, which is the other thing I do. So societal networks are networks that we use in society. This is a bit like what John was saying, that type A network and type B network are beginning to interact. One was human and the other was technological. Here it's networks of the type that we use every day interacting with networks of the type that we've been studying, in sort of computer network sense. So these are all networks, and the reason it's interesting to us, I believe, is that because it allows us to consume or dispose of resources through a combination of technological mechanisms and human actions. And the human actions part is extremely key in these cases, because that's where the efficiency, that's what's affecting the efficiency. So for us, it's a nice activity to jump into, I believe. And I have examples and stories to tell you. I'll tell you 3. But to continue along this thing, you have these old networks, which have been around a lot longer than these other guys who've shown up more recently. We've spent an enormous amount of time thinking about these things, so they're obviously very sophisticated, right? So every time you go to one of these old networks, this is some language I picked up, right? You go to one of these old networks and touch it up with one of these new guys, and then you get to call it smart, right? Smart roads, smart grids. So those are dumb without these guys, basically, okay? So you put this arrow and suddenly everything becomes smart. And of course, for us, we've got a lot of architectural principles here, like the end-to-end principle and various other things that we've thought of several for 2 decades now, let's say. And that can be imported there, and that hasn't happened. And then, of course, as a method to give commuters information or electricity users information in a more real-time way, you could do these smartening, so to speak. And then it allows us to deploy economic incentive mechanisms. And that's what's interesting about this interplay. Okay? And there are projects that we worked on, transportation projects, where people are paid money to travel in less congested times. And that's the way we want to combat congestion. And we've done this as a pilot in Infosys in India, Bangalore, 20,000 people involved in that experiment. And it was successful in getting the commuters to come earlier, which, of course, the management loved, right? And so it's going to be at all 8 of the Infosys locations shortly. This is the talk I gave on Monday. There's congestion at Stanford, which looks like this. There's a reduced peak hour trips problem at Stanford campaign. And we're going to have its technology meets economics. And then public transit systems are always capacitated for peak use, and you get overcrowding in the peak time and serious undercrowding in the off-peak time. And again, we'd like to load balance these public transport buses. And so here's a story. I'm not going to tell you about how to load balance that. That's a project that's longer to describe. But I'll give you a different example. Bangalore Metropolitan Transportation Corporation, BMTC, introduced with great sort of fanfare, I think quite rightly, an all-day pass. You go buy this thing, it costs 32 rupees, which is like 60 cents, and you can travel from 6 in the morning to midnight. Okay, so this has had the consequence of one guy buys it at 6 in the morning, takes a trip, costing 25 rupees, gets off on the other side, immediately sells it to somebody else for 20 rupees. Okay? And so this ticket is resold on average 6 or 8 times. There's probably a power law distribution somewhere there. Okay? And you can stand in the line to get a ticket, and you get accosted by these, what are they called, hawkers? No. The guys who sell tickets at games and stuff, the black market type. So you get sold at like 3 p.m., it's at 14 rupees. So there's a secondary market that's developed. This represents a lot of revenue for this bus company to the order of 300 to 500,000 rupees a day. And that's pretty significant. And when I was giving a talk like this in Bangalore, somebody else spoke to me later and said, how do we incentivize people to not do this resale business? And I take the same point of view that John takes. We can't possibly view resale or corruption in moral terms in these cases. We set the rules up like this. There's nothing prohibiting this person from doing this resale. And so one of the things that we want to do is luckily these bus tickets have a unique number. We're going to make them lottery tickets. So we'll draw from those numbers, and if you hold the ticket, then you get the prize. So there's an incentive for you to hold on to your ticket and not to sell it. Okay? It's a simple but nice example. Okay? So this is something that we've actually got approval from the managing director of this company to do. And sometime at the end of spring, this is going to start. So we're trying to form a center at Stanford. Because, there's a collection of problems. I'm not telling you all the examples. You already heard me speak about it on Monday. So there are these are some of the scientific board members that have agreed to be on the board of the center. So hopefully we will have, and they all have something to do with transportation or climate change or something like this. So in another minute or two, let me run through this one slide on data centers. So this is about 70% of what I do now. It used to be 90% of what I did. Since last year, this other guy, Societal Networks, has grown to become 30%. Okay, so and I'm going to take the same approach to this in science we do. There's two ways of thinking about it, right? There's theory building and there's problem solving. I'm going to take the problem solving approach to say this bottom up examples. Okay, so if you think of examples, there are problems, and then hopefully that explains what sort of theory is needed. Let's look at these data centers. What are they? How many of you have heard of data centers? Okay, see, this is an information theory meeting. In networking, everybody's heard of it. It's not. It's in the news and so on. But the thing is that they're the back end. They're the things that sit behind your Facebook website, right? And for example, Facebook has, in fact, the number 30,000 is one of their data centers. I think they now have 7. And they are the engines, in a way. They are the switches, routers, storage, etc., that power Google search type data. There are many types of data center. Google's is, say, optimized for search. There are Facebook, Twitter-type social networking data centers. Cloud computing, this is the Amazon's EC2 system or Microsoft's Azure system. Shopping, Walmart, etc. High-frequency trading. You must have heard of these algorithmic game theorists, algorithmic traders. Okay, so the human being is no longer trading, it's an algorithm that's doing the trading. You just sort of scan the sticker tape and make your bets, like in extremely small durations of time. And so it's really interesting because look at the numbers here. I mean, there's very large numbers, so the size is now big. So this thing behaves almost sometimes as it wants. And what's also interesting, for example, is that the human beings that are using this, like Facebook, here's another example. This security, privacy, and social networks. You can now put 1,000 photos from a trip you took, because these photos are easy to take. They're all digital photos. And you can have them uploaded. And you can go to each one of them. And you may have 500 people who are in your social circle. And you can decide, photo number 1 cannot be seen by these 35 people, but can be seen by the remaining people. Okay. Photo number 2, a different subset. So there's a binary bitmap of zeros and ones, which indicates who can see this image or not see this image. Okay, so your parents may not be allowed to see some things, whereas your friends may be allowed to see some things, right? So this sort of thing exists. And so this has become a massive problem for Facebook. And they don't like, they've given this as a feature, but they don't like it, okay? Because who doesn't like it is not the front-end guys, it's the back-end guys. It's the guys that run this stuff find it extremely difficult because their service level agreement is they're now up to delivering the content back or the page back to you in about a second. And they say second, and I think it's at 1.5 seconds. And I think they're failing several times. You can post your photos and you don't see it immediately. And there's very nice algorithmic network design, architecture type questions just for dealing with problems like this. And then, of course, there's this lurid thing I read on the web about that high-frequency trading is described as millions of dollars in milliseconds. Okay, I thought like that's too catchy not to put on these slides. But you can imagine these traders, these sort of people with hairy knuckles who you don't want to mess with, right? That guy's breathing down your neck, and you're the guy running this network, and some trade just didn't go on time, and that lost a few million dollars. So this is actually true. That this last thing I told you, there are people out there building networks so that high-frequency trading can take place at the speed at which it wants to. And but of course, I used to teach a course called Network Algorithms. I thought, well, let's call it Network Science. This is what I did last year, but also with a view to making the front and the back ends meet. I used to teach the algorithms that show up in switching and so on. But of course, this other thing is very interesting. And Amin Saberi, my colleague, teaches this course called Information Networks. And we're combining these two courses into one thing and calling it Network Science. Thank you.
Since we are running out of time, I think maybe we should open the floor to the questions from the audience. There are mics that our student volunteers can bring to you if you raise your hand.
Oh, there.
So the examples were very intriguing and very interesting, especially this combination of, when there is a clash of human networks with the technology networks. So it appears that most of the current work is in understanding or modeling it. Is there already success stories where the models have actually predicted something which would happen and it didn't happen? So is the predictive power already? See, the one reason for modeling would be that you can predict things. Is there already something you have witnessed, or there are some examples which have?
I mean, that's a good question. Right? So the question of the predictive powers. Actually, I think there are sort of two questions here. One is examples where it's been used in a design context, where you designed the system a certain way because you predicted something, and another where you simply made a prediction about the world, whether or not you built it in. I think that there are a few examples of each, and I mean, to pick one example, I'll pick one from Dimitris's tutorial yesterday, which I'm picking only because I know it since I was involved in it, but there are other many good examples by other people, which is if you look at the searchability of social networks, so things like Stanley Milgram's 6 degrees experiment, and if you build a simple random graph model, as Dimitris showed, it predicts that if you're going to have searchability, then you should have a certain density of friends at each scale of distance, say geographic distance or social distance, right? That searchability implies a certain arrangement of these links across distance scales. And that was a completely theoretical prediction, which first of all, when it was made, it wasn't clear how you would test it, because it seemed like at the time you'd need to get some system where you could somehow convince 10 million or 100 million people to all log in, say where they lived and who their friends were, and who in the world would do that, right? But of course, 5-10 years later, we have Facebook, where somehow everyone by consensus agreed to do that, and so you can test this. And the second surprise was that not only do you have the data to test it, but actually, after you correct for non-uniform population distributions, which is an important technical wrinkle in the model that needs a new theorem, you actually get an amazingly good fit. And this was first done with smaller systems like LiveJournal, where you got a very, very good fit. And then it was done with an order of magnitude larger systems like Facebook, only within the past few months. And you see this incredibly good fit to the theoretical prediction for what you would need in order for social networks to be searchable. And so what's strange is that at some sense is a kind of satisfying confirmation of one level of prediction, but it raises an equally vexing question one level down, which is whatever people are doing on Facebook, they're not trying to configure their world to make the Milgram experiment possible. They're there to post photos from their vacation and reconnect with friends and who knows what. And yet, somehow accidentally or organically or emergently or whatever adjective you want to use, the network has arranged itself to do that. What the selective pressures are causing that to happen is a whole new level of open questions, but it's one that we can only ask because somehow a first level of predictions got confirmed.
So the experiment we ran in Bangalore, we were just pretty much using, there's a paper by Vickery from '69, which talked about the need to price road congestion. And then he also did Vickery auctions and stuff. So all we did was just come up with an algorithm that merged these ideas and came up with this incentive mechanism where you would just earn points, and points would equal rupees, right? And yeah, it worked in a way quite well. It was pretty successful. The company's going to now do it in all of their branches in India. There are surprises, though. I mean, in the large, the theory may work, but people do funny things. And so that's another thing that we've learned. And some behavioral economist who heard me speak about this said, do you have ethnographers in your team? I don't even know why we would need these ethnographers. Are different, types of people going to behave differently? I mean, I didn't understand the relevance at the time. And it was more along the lines of people who are single and people who are not, they behave slightly differently, and what's important. So these are the things I think that the human element seems pretty strong. And it's you can't just design these algorithms in open loop, it seems, obviously. So we had some feedback to the form of a bulletin board, which kept us busy. We got some 3,000 to 5,000 emails. It was a really fun experiment. Enjoyed it. Let's see how the others go.
I had a question about the bus experiment. I was curious, did it actually cause some load balancing to sell these tickets that lasted longer? Was that the original goal? I mean, because you can't use the same ticket at the same time, so it might load balance as well.
Oh, you mean the day passes?
Yeah.
No, that was day passes was meant to help tourists. This is really what they thought, that the regulars wouldn't be traveling in the bus all day, so we don't lose on them. They came up with a number, 32 rupees, thinking if a person, a Bangalore native, bought the ticket and took one trip to work and one back, that they would just spend 32 rupees, which would be fine, but they were trying to help the tourists, which are less than 0.1% of the commuters. But then they had this extremely unintended consequence, and they don't know how to, so that's what happened there.
Do you think this could also cause some kind of load balancing, though, that people can't use the same ticket at the same time? It's going to actually spread the commuting hour out some, or no?
No, I think the load balancing is more people have a preference for traveling in peak times. So around 80% of all commuting in just any urban area takes place in an hour and a half or two period. It's the same people going from the same place to the same other place and back again in the evening. That's urban congestion. That is going to happen, and you just want to see if you can jitter that and smear the load out a bit. So it's a different.
A question regarding the economic top-down modeling. Oh.
There's first one down here.
So there was a study, I don't know if you remember, many years ago in the public transportation in the San Francisco area, and the consequence of this study was remarkable. If you consider all the costs to society of transportation, it's much, much more effective to give transportation for free, and rather than live with the illusion that you're going to have self-supporting and all that. So in your example, I would suggest I calculate carefully what resources I need. I allow them for free, no tickets, no second market, nothing. So, but this requires that you do what in system engineering we call total cost of ownership. In other words, you don't just take the isolated system of transportation, you consider all the other costs.
Yeah, I think this is, some cities have done this, notably, I think Medellin in Colombia, they had a visionary mayor who did this, thereby claiming the streets back. This was an amazing strategy. If I make the streets be very easily, cheaply, zero-cost accessible, then I can get the gangsters out, right? And but his motivation was that. So he made it free, and it was very successful. It didn't go away, in other words. The New York City subway system, $1 flat, no matter what the distance. That was another radical suggestion by Vickery, in fact. I made all the boroughs grow and everything. So this is. So I've asked this. It's a big. The Bangalore system is the only one that actually. Well, I know it's amongst the big cities is the only one that actually runs on profit. And I don't think they can. Most of the others are subsidized by the state. And the quality is pretty poor when you make it free, especially, that's what I've heard at least is true in India. So it's not clear. It's some policy.
There is profit from the finances of transportation system, but there's losses in terms of pollution, all the other things that people are using, and social anxiety. So if you really think about the whole system, it's debatable whether any of these philosophies of keeping and things like David Washington, all the costs associated with that make any sense.
True.
There was one question from the back about top-down modeling. Yeah, down there.
Oh, so you mentioned that there are cases for economists where their top-down models have inconsistent predictions within the system. And do you have an example? Because it's hard to put my head around that.
Oh, okay. Yeah. Right. It's a question, what do I mean by inconsistent predictions? So for example, there's this challenge if you want to, say, take two models from economic theory. One is, say, Nash equilibrium for games with small numbers of players. Another is the theory of competitive equilibrium, like Arrow-Debreu market equilibrium, for example. So one thing that, the computer science types like us have advanced as a complaint about market equilibrium is that there's not a strategic aspect to it, as in market equilibrium is a set of prices that clear the market, but you can create situations where someone might want to deviate from that and do better for themselves. Right? So there isn't anything compelling the sellers to set those prices, and if certain sellers deviated and set different prices, they would personally do better, and the prices wouldn't clear the market. So, so this is. You could also find more sort of specific, but it would take longer to talk about examples where there are direct mathematical conclusions that may be in conflict. But this is one that's sort of very clearly qualitatively in conflict. One, that we should be in some kind of equilibrium where no one can strategically change what they're doing to improve their outcome. And another, the theory of competitive equilibrium, which says prices tend to be set so that they clear the market. Both of these theories are somehow useful because what competitive equilibrium is not so much an operational theory of how people behave, so much as a descriptive theory of how markets function in normal steady-state operation, right? And so I think that's something that we don't have as much, say, in computer science or in engineering type disciplines where we build the things, is a descriptive theory that we know doesn't have quite an operational basis in the micro-level components, and yet tends to describe the way the thing functions in normal operation. Right? We're starting to see those descriptive theories when we have, large, complicated networks of the kinds that Topology or that Don were talking about. Right, but that's an example where the micro-level models you make of individuals interacting with payoff matrices doesn't necessarily align with the descriptive models you make up at a macro scale.
Okay, so since it's time to start the other sessions, I would like to conclude with just one last question to the panelists. Since they are non-information theorists and we have an information theory audience, I would like to know if they see a place for information theory in building network science. And that would be the last question. Is there anyone in particular that wants?
Don, do you want to go?
Don.
So, I mean, speaking for myself, certainly when I think in terms of like the kind of data to collect it and what to do with it, I'm very much interested in data that will provide the maximum amount of information for, let's say, sort of answering the query at hand. So certainly things like Fisher information, Bayesian information, and other variants, I think, play a really important role there in terms of being able to sort of design appropriate measurement structures.
Thank you. I'll take that as a yes. With that, I conclude the panel.